Pleasure to be invited here. I'd just like to say that one of the things we've all learned over the last couple of years is how important it is for us to meet in person, and that sitting at home and working is not a substitute. So it's a pleasure to be invited here, and the notes I'm going to be working from are here. You can just download the PDF file. It contains sort of rough notes for the talks, as well as the problems. I assembled probably too many problems, and they range in difficulty from probably too easy to probably too difficult. Find some that you will benefit from working on and work on them, I guess. Janina Letts is actually doing the problem session after this lecture. So what I'm intending to talk about is sort of module categories for finite groups and how to apply spectral methods to those. And I need to start by telling you quite a bit about the group algebra and the cohomology of groups. So that's how I'm going to start. I'm not quite sure of the speed I should be going at. So slow, is it? Julia says slow. So I'm at least going to start slowly, and if you want to slow me down or speed me up, just say so. So we're going to start off with, I'm going to be working always over a field of characteristic P, and G is a finite group. And so the first object of interest is the group algebra KG. So this is, so it's just a vector space whose basis elements are identified with the group elements, and the multiplication just comes from the group multiplication extended bilinearly. And so this is a finite dimensional algebra. And we need to look at various properties of this. The first one is that it's self-injective. And what this means is that projective modules are exactly the same thing as injective modules. And I should probably give you a sort of visual indication of what these projective and injective modules look like. So a projective indecomposable module is the same thing as the projective cover of a simple module. And this actually gives you a one-on-one correspondence between the isomorphism classes of projective indecomposables and the isomorphism classes of simples. So the structure of the projective indecomposable is that it's got a unique top composition factor, which is that simple module. Then it's got some stuff in the middle. And then at the bottom, it's actually got a unique composition factor because it's an injective indecomposable. But the fact is that this is the same simple module at the bottom. And then, I mean, there are some degenerate cases, like some simple modules are actually projective already. If anyone talks to you about blocks of defect zero, they're these projective simple modules. And then there are, this middle may actually not exist at all. You can just have two copies of the symbol glued together like that. So those are the basic models for the structure of a projective indecomposable. Any questions so far? No, good. So the other piece of structure is that the group algebra is actually a Hopf algebra. So it has a co-multiplication, which I'll write as delta, and it's simply, so this is a map from kg to kg tensor kg, and it is defined on the basis of group elements just by repeating the group element. And then there's an antipode called sigma from kg. So I should have this higher, shouldn't I? I remember from this morning that actually the back of the ball could not really see very low. So this is given by sending each group element to its inverse. And these give the group algebra the structure of a Hopf algebra. And this is what tells you how to tensor modules. So if you've got two different modules, you can make the tensor product of module over kg tensor kg and then pull back to give a module over kg. So this is a finite dimensional Hopf algebra. It's not commutative unless G is commutative, but it is co-commutative. This is a symmetric thing to do. So, so the dual Hopf algebra is called the coordinate ring. It is written like this. That's commutative, but not necessarily co-commutative. So you might like to think of co-modules over this one. And that's all I'll say for now about the structure of the group algebra. But these properties will actually come back to haunt us. Next, we need to talk about cohomology. So, there are several different views of group cohomology according to whether you're, let's say, an algebraist or a topologist. And so the algebraic definition is just that the cohomology of G with the coefficients in a module is just X star over the group algebra of the trivial module with the module. So this is the module where all the group elements are just acting as the identity. So what do? You take your resolution of K. Actually, let's just write up how to look at X star Kg of Mn in general. You take your resolution of n by projective modules, and then you hom into n. So you take hom sub Kg of P0 into an n, and then the maps of course go the other way. And you take the cohomology of this complex. But we also want to talk about Tate cohomology. And this is where the fact that projective modules and injective modules are the same thing really starts to become important. So for Tate cohomology, in order to define X hat star Kg, you don't just take a projective resolution of M, but you also take an injective resolution and you tack them together. So let's label these P minus 1, P minus 2, and so on. So this is a doubly infinite exact sequence of projectives. such that the image of the middle map is your module n. And then you take hom pi n, and of course that maps to hom p I plus 1 into n and so on. And you take the cohomology of that complex, and that is the Tate cohomology. So in positive degrees, it agrees with x. In degree 0, it's slightly different. And in negative degrees, it actually has to do with Tate duality. So what is Tate duality? Well, in order to obtain an injective resolution of a module, if the module were finite dimensional, I could just take a projective resolution of the dual and dualize it. So for finite dimensional modules, there's a duality which says x hat star kg, well, x hat n kg of mn is the vector space dual of x n, what is it, minus n minus 1 kg n m vector space dual. And actually you really only need, what is it? You need n to be finite dimensional. You really don't need m to be finite dimensional. Have I got that right?
Do you need some stars on your M and N as well? No, okay.
No, I don't think so. I think it's correct as, yeah. Yeah. You may wonder where this minus 1 comes from. Well, you'll notice that the projective resolution started with 0 and the injective resolution started with minus 1, which is sort of one off. Okay, so that's what you do if you're an algebraist. If you're a topologist, you do something slightly different. You let EG be a contractible space with a free G action. You let BG be the quotient by that action. And then the point here is that actually the chains on EG, the coefficients in, yeah, that is a free resolution of K over Kg. So just because, since G acts freely on EG, it acts freely on the, let's say, the singular chains, whatever you like. So the cohomology of BG, which is the cohomology of, how do you take cohomology of a space? You take homs from the singular chains into K. Have I got enough brackets? No. Right. Yes. And then you think of this as hom kg of E. Ah, that's because I didn't put in chains. That's why I didn't have enough brackets. Good. So hom kg of chains on EG, K into K. And now you're just taking homs of free resolution into K, so that's X. Kg, Kk. So the cohomology of this space is actually X over the group. So that's actually what we usually write as cohomology of the group. So there's a little notational thing here. When I write cohomology of a space, I'm going to use a semicolon. When I write the cohomology of a group, I'm going to write a comma. Well, it matters. Are there any questions so far?
Or maybe whether you want to make a topological definition of any coefficients.
Oh, sorry?
The algebraic definition is for any coefficients, the topological one is only for the.
Yeah, so if you want to know how to do H star of PG semicolon M, you have to make M into a local system of coefficients. So you have EG cross M, and then you quotient out the action of the group on both sides. So let's do an example. Well, if I take the infinite sphere with just regarded as the union of the finite dimensional spheres with the weak topology, then that's actually a contractible space because each sphere is the equator in the next sphere up, and it slides up to contract to the north pole, as it were. So this is contractible. And the cyclic group of order 2 acts, I hope everyone knows the word antipodally. In other words, it sends England to somewhere just southeast of New Zealand and so on. And so the quotient is S infinity mod the cyclic group of order 2 is just RP infinity. And so H star of the cyclic group of order 2 with coefficients in the field of characteristic 2 is the cohomology of RP infinity, which is just a polynomial ring on a generator of degree 1.
Why do you need a field to be characteristic so?
In any other characteristic, the cohomology of this space vanishes.
Okay.
Over the integers, it's actually the generator is in degree 2.
You might want to write K with a second, the middle you want to.
Oh, sorry. Like that. So then we have a Quillen theorem, and if we apply that to an elementary abelian group, in other words, a group that's just a direct product of cyclic groups of order 2, we'll get a polynomial ring. And now I realise I really wanted this to be the letter V, for reasons which may or may not become obvious. So this will be a polynomial ring in variables V1 up to Vr, still of degree 1. And while I'm at it, I should tell you what happens for an odd elementary abelian group. How was I able to do this without making everything invisible?
I wasn't.
You weren't, okay.
I didn't go further than this.
Can I write one more line? That's still visible? Good. Okay, so for P odd, I do need to tell you what the cohomology of Z mod P to the R, the coefficients in K is. And then K in this case has characteristic P. So you get an exterior algebra on some elements U1 up to UR and a polynomial algebra on variables V1 up to VR. And the degree of the UI is 1, and the degree of the VI is 2. Since I'm talking about this as a ring, I should explain how you multiply cohomology elements. So cut products. Now I'm going below the bottom, sorry. Is the same as Yoneda products in X. So you just take an exact sequence representing the element of X and you splice it to another exact sequence to get Yoneda products. But because they also have a cut product definition, it's actually a graded commutative ring. So this makes H star of GK graded commutative. Graded commutative means that Yx is minus 1 to the product of the degrees xy. In particular, if you quotient out the nil radical, it's a commutative ring. So at this point I should give you a warning that for a non-trivial module, X star kg of Mn is not necessarily graded commutative. Even if M is simple. So you can actually cook up examples of simple modules over finite groups where the X string is not graded commutative. So we can avoid many a mistake. the next thing to know is the Evans-Venkoff theorem. This says that H star of GK is finitely generated as a K algebra. The actual statement of the theorem also includes the fact that if M is finite dimensional, then H star of Gm is a finitely generated module over H star of Gk. And indeed, if you have a pair of finite dimensional modules, then X is finite, X to Mn is finitely generated as a module over the cohomology ring. Okay, so far so good. And now we come to the work of Quillen. It seems to appear in every lecture. Part of the reason why I explicitly told you the cohomology of elementary abelian P groups is because of Quillen's theorem, which is as follows. Let's write A sub P of G for the category whose objects are elementary abelian P subgroups of G, and whose arrows are given by conjugations composed with inclusions. So if you have two elementary abelian subgroups of your group, you might be able to conjugate one into the other and then include it. And then what you do is you take all these elementary abelian subgroups and you take their cohomologies and you take the limit over this category. There's obviously a map, a restriction map from the cohomology of the group to that limit. And Quillen's theorem states that this is sort of close to being an isomorphism. It's not an isomorphism, but it's what's called an F isomorphism. Which means two things. It means firstly, if X is in the kernel, X is nilpotent. So the elementary abelian groups detect whether an element in cohomology is nilpotent. If something is nilpotent on restriction to every elementary abelian, then it's nilpotent. But secondly, if y is in the limit, there exists there exists n such that y to the p to the n is in the image. So in other words, another word for F isomorphism is inseparable isogeny. And these are the things in characteristic P which exactly give you an isomorphism at the level of sets on the point spectrum, the spectrum of this ring. So in other words, if I look at the spectrum of this ring, which is some affine variety, the maps go the other way? Yeah. So this will have to be that way. This map is an isomorphism at the level of sets of points. So let's think for a second about what this means. If you've got an elementary abelian group, so its cohomology, if you ignore the nilpotents, is just a polynomial ring. So the spectrum of that is an affine space. So what you're doing here by taking this limit is you're taking all those normalizers of those affine spaces and quotienting out the variety, the affine space, by the action of the normalizer, and then you're inserting them into each other through the inclusions. So that's the conjugations and the inclusions. They fold up the affine spaces and then include them, and that's the way it's glued together.
Is this map actually a homeomorphism?
It's a homeomorphism. Is that the right symbol for a homeomorphism? No idea. So let's write down some consequences of this. So first consequence is that we can now see what the Kroll dimension is of the cohomology ring, because we've got it explicitly displayed in these terms. So all you need to do is look for the maximal size of an elementary abelian P subgroup. Its rank is the Kroll dimension. So the Kroll dimension of H star of G comma K is equal to what's called the P rank of G. So the P rank just means the rank of the largest elementary abelian P subgroup of G. So the next thing to warn you is that the Evans-Venkoff theorem does not apply to Tate cohomology. So if you look at Tate cohomology, let me give you a misleading example first, and then tell you what happens more generally. So if you look at the Tate cohomology of the cyclic group of order P, with coefficients in characteristic P, let's just do the cyclic group of order 2, actually. That's an easy case. So this has characteristic 2. Well, you remember the thing above was just a polynomial ring. Well, this just gives you Laurent polynomials. So you've simply inverted this element B. However, if R is bigger than 1, all elements of negative degree multiply to give 0. In other words, if I take any two elements of negative degree and multiply them together, I get 0. So in particular, this is not a Noetherian ring. So somehow what's happening is you've got the positive cohomology, this stuff, and you've got the negative cohomology, this stuff. So here's 0 and -1. So if the rank is bigger than 1, what's happening is that this is the dual of that module, but it's a trivial extension. So everything here squares to 0. And if you've got something of positive degree and something of negative degree, and you find the product, if the product ends up in positive degree, it's 0. If it ends up in negative degree, you just calculate as though this was the dual of the positive degree. So I should also write H hat star of Z mod P, the coefficients in characteristic P, which is, you remember we had this exterior algebra, and then you've got K of the inverse, where U had degree 1 and V had degree 2. So for rank 1, you get what you might expect. For larger rank, this is really quite different. Then the next thing to tell you about is Chouinard's theorem. Which is closely related to this theorem of Quillen. It says that the Kg module M is projective if and only if for all elementary abelian P subgroups E of G, M, the restriction of M down to E is projective. So in other words, you can detect projectivity on elementary abelian subgroups. And these two theorems are so closely related that you can actually moderately easily deduce each from the other, if you work at it. Yeah, so let me give you an example of this. Let's say you have the quaternion group of order 8. All right? Let's think what the elementary abelian P subgroups, 2 subgroups are. Well, there's just one. There's that central involution, and that's it. So if you have a module for the quaternion group of order 8 and you want to know whether it's projective, you just have to restrict down to that involution. Let's say that involution is called Z, or maybe Z. So if the module were finite dimensional, you would just have to calculate the rank of 1 plus Z, acting on your module, and see whether it was exactly half the dimension of the module. So if it's half the dimension of the module, then you're projective. And if the rank is less than half the dimension, it's not projective. What do we do, Tom? 20 minutes left? Is that right? Yeah, good. Oh, we're getting. Any questions so far? Yes.
Can I ask a question, sir? This might be a long question, but I don't know if it makes sense. Is there any connection with that Quillen's theorem with the Hopkins Smith theorem from the Quillen's theorem? Like, is there some analog, some dictionary, like some way to write it down to say?
So we'll talk about some things which are related to that Hopkins-Smith theorem later on. It's not quite this, but it's related. Any more questions? Yes, so so we're gradually working up towards things called pi points, but we're getting there slowly. The next step in the development is Dade's theorem. So this tells you, we've just seen that it's really important to be able to understand whether a module over an elementary abelian P group is projective. Here's how to do it. Dade's theorem tells you the following. Well, let's start by naming some generators for the group. So this is supposed to be your elementary abelian P group. And I'm going to write xi for gi minus 1 as an element of the group algebra of the group of the E, yes. Okay? So we're in characteristic P. Gi to the P is 1. So gi minus 1 to the P is 0. Right? Is that thing with binomial coefficients? So actually, I can write Ke as a truncated polynomial ring in these xi. Okay? So the statement of Dade's theorem is if K is algebraically closed, and this is important, and M is finite dimensional, this is also important, then M is projective if and only if whenever I have a non-zero point in affine space, so for all lambda 1 up to lambda r in affine R space, and I better make them non-zero. When I restrict for notation, I'm going to write x sub alpha equals lambda 1 x1 plus lambda r xr. So just the linear combinations of the x's. All right? If and only if, for all alpha, the restriction of m to k of x alpha, you'll notice that x alpha still has order p, like that, is projective. So just as a module for this truncated polynomial ring on just one generator, whose p power is 0. And of course, that's the same as asking whether the rank of x alpha on M is just p minus 1 piece of the dimension of M. So this is called the rank condition for being projected. Okay? So what we do is...
What do you mean by the rank of x alpha?
So x alpha is an element of the group algebra of E. So you look at the matrix representing it on the module M, and you take the rank of that matrix. So it's at most p minus 1 over p of the dimension of M because its p power is 0. If you just think about Jordan canonical form. So this leads to the definition of Carlson's rank variety associated to a module. So the rank variety, and here R stands for rank rather than the rank of G. So it's not a number, it's just a letter R. You can't make this distinction in Russian, by the way. Trying to make distinction between rank and the rank doesn't make sense. The rank variety of M is the set of alpha in affine space such that M restricted down to k of x alpha modulo x alpha to the p is not projected. And we also chuck in 0 because we excluded it over here. And so what you can see from what we've just said is, well, you're computing ranks of linear combinations of elements. And a point is in the variety if and only if the rank is smaller than this number. So you take all the minors of the matrices, and those give you polynomial equations expressing that rank condition. So the minors of this size of that matrix define a variety, which is this. So this is a closed. You also see that these polynomials that you get that way are homogeneous. So this is a closed homogeneous subvariety of affine R space over K. So that's called the rank variety. And it has some good properties. So a question?
Yeah, I'm sorry, I didn't get why it's homogeneous.
So each of these xi's is being represented by some matrix, and I'm taking linear combinations of those, and then taking a determinant. So that determinant will be of this degree in the R variables.
Okay.
Is that making sense?
Okay.
So you're just multiplying linear. You're multiplying that many linear terms and then adding a bunch of that, things like that.
Yes, okay.
Yeah. So the rank variety of a direct sum is just the union of the rank varieties. And so this is a property that's fairly easy to prove. What's much more difficult, and took a while, the RE of a tensor product. This is the tensor product over the field as defined using the Hopf structure. Is the intersection. So if you like, this theory of rank varieties is quite a good tool for seeing whether tensor products of modules are projective. You just have to intersect their rank varieties and see whether you get zero. So Dade's theorem can be expressed as saying that the rank variety of M just consists of zero if and only if M is projective. And actually, another property that's worth knowing, but I won't write it down, is if you take a minimal resolution of M over the group algebra, the rate of growth of that minimal resolution is a polynomial whose degree is exactly the dimension of this variety. Well, in the following sense. So I'm thinking of something that's periodic as being polynomial of growth 1. And if it has linear growth, I'm thinking of it as having growth 2 and so on. So it might be one more than the number you might be expecting. So the next property is that every closed homogeneous subvariety of affine space occurs this way. So given an elementary abelian group and a closed homogeneous subvariety of its corresponding affine space, you can construct a finite dimensional module whose rank variety is exactly that variety. So, I mean, in a sense, that tells you the theory of modules is at least as complicated as the theory of subvarieties of this affine space.
Is it appears this way for X? Oh, yeah, it's okay. Yeah, thank you.
Yeah, it's the same R. Yeah. Yeah, and also for notation, I'm going to write V with a bar over it for the corresponding projective variety. Projective subvariety of P R minus 1 of K. Because it's homogeneous, you can just sort of squash it down and make a projective variety of one dimension smaller. So we have 5 minutes left. Yes?
The field K is the characteristic P everywhere, right?
Yeah.
Okay.
This is, yeah. I should have said here K has characteristic P and is algebraically closed. Yes.
Do we get every projective variety as a V bar?
Yep. Yes. So so what we want to do next, and I'll spend just the rest of this session describing it in words, and I'll do it next time, is we want to do this for infinitely generated modules over non-algebraic closed fields. And you may wonder why. Well, okay, let me give you first an analogy and then a concrete reason. Let's suppose you're only interested in finite dimensional manifolds. And let's suppose that you started working with various cohomology theories like ordinary cohomology, K-theory, and so on these finite dimensional manifolds. Well, those theories are representable, but not by finite dimensional manifolds. You have to go to not just infinite dimensional spaces, you have to go to spectra, right? So even if you're only interested in finite dimensional manifolds, you're forced in some sense to look at spectra. Here, if you want to look at the module category and various functors on it, and you want to make them representable, the representing objects are going to be infinite dimensional modules. And there are some very specific infinite dimensional modules that come up this way. And I'll describe them explicitly. But they are what pulls the module category apart into these spectral layers. The sort of, for modular representation theory, these layers are going to be the analogues of Morava's K-theories. So those Morava K-theories are the sort of smallest layers you can make out of homotopy theory. Here, they're going to be the smallest layers you can make out of the module category. And I think that might be a good place to call it quits for today.
But we didn't explain why algebraic close is dropped.
First of all, because you can. And often you're confronted with fields that are not algebraically closed. But also, even if you're algebraically closed, we're going to need to look at field extensions that are transcendental over the original field. You're forced into looking at that in order to get enough generic points for varieties. And once you've started introducing these infinite extensions for generic points, algebraic closure no longer is relevant, really. And so it all works without the algebraic closure, but we need to modify this Dade's lemma in order to do that. Any other questions?
Maybe we should think first.